Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. So far in previous videos, we have covered the theoretical background related to travel demand modeling. In this video and upcoming videos, we will look at how these theoretical backgrounds are implemented within the travel demand model under section 3.4, and then under section 3.5, which will be new videos, we will look at how these travel demand models are used, what procedure process the output from travel demand models. So in 3.4 we are looking at how these models are developed and implemented, and in 3.5 we will be looking at how to use them. So from a traffic engineer perspective, I'm guessing 3.5 will be more important than 3.4, which is more important than 3.3. So since we are more focused on the user side. So before looking at how they are used, we must need to have a good understanding on how these models are built. So let's get started. Travel demand model is needed to forecast future traffic volumes and plan for future transportation infrastructure. Like I mentioned, the majority of State Department of Transportation develop their statewide travel demand model, and for major cities, typically over a population of greater than 50,000, local metropolitan planning organization are responsible for developing their travel demand model. So, like I have mentioned in video before, cities with a population greater than 50,000 are called metropolitan cities, and they have the planning organizations called MPOs, a metropolitan planning organization, and they develop their own travel demand models. So what we have is, if I can draw very crudely Texas, please ignore my drawing skills with mouse. So if I can draw Texas here, somewhere like this, then we have a major metropolitan area, Dallas and Fort Worth here, then we have Houston somewhere here, then we have Austin where I'm located, this is another metropolitan area, then we have San Antonio here, then we have El Paso here, and then we have Laredo. So let me Laredo somewhere here. So these are some of the metropolitan area in Texas. So what happens is the MPO, which are for that specific metropolitan area. For example, for Austin, the MPO is called Campo. For San Antonio, I think it's called Alamo. For Dallas, I think it's called NCT COG. For Houston, it's called HGAC, Houston Galveston something Council, and then El Paso MPO and Laredo MPO. So these MPOs, they build their own travel demand model, which is very detailed. It has future transportation projects coded in it in very detailed format. So it has more arterials and local state and is pretty detailed. Then there is a statewide travel demand model, which is generally developed by state DOTs. So in this case, TxDOT has statewide travel demand model called SAM, which is, I believe, is developed at TTI, Texas Transportation Institute, but I may be wrong. So most of the state DOTs have something called statewide travel demand model, which looks at entire state, and they are very helpful to do the travel demand analysis for the rural area. And most of the bigger cities have their own travel demand models. So most of the state travel demand models uses four-step TDM method, whereas the bigger cities typically can use activity-based models, or they can use four-step travel demand models. So for Austin Campo, we use four-step travel demand model, and for others we might be using activity-based travel demand models. So in my personal experience, if a city has a lot of transit and people go from, let's say, their houses to take a transit and then transfer somewhere, and when the trip is broken into multiple pieces using different mode of transportation or different routes, then activity based uh, travel demand modeling is used. But for most of the travel demand, we use four-step travel demand model. So kind of this is just brief overview of what kind of models are out there, and just a brief introduction on how these models exist and who build them. Now let's look at some data sources. So statewide travel demand model uses established regional models, which is MPO models, and national census data. So when we are building the statewide model, we look at the local MPO model. Not we, there are only few consultants who actually build the travel demand models, and they are very specialized in building the models. Not a lot of consultants build the travel demand model. Is a kind of a very specialized job to build the travel demand models. So if we are building a statewide travel demand model or travel demand model for a larger region, then we can use the local MPO models, which are regional models, and national census data for all other areas of the state. When MPOs are building their model, so MPO model use long range socioeconomic data and local land use plan. Because MPOs models are detailed, we are looking at land use plan level. TDM are generally built either using TransCAD or Cube software. Now there is a new software in play by Florida DOT, which is Visum. Florida DOT has moved from TransCAD to Visum recently, and we will see how this expansion to Visum plays out. But they are generally built either in TransCAD or Cube software. In this book, in this video series, we will use the travel demand model using TransCAD for consistency. So we will use the file format, we will use the structure using the TransCAD software, just for the simplicity. That does not mean one software is preferred over another. It's just for consistency, we will use the TransCAD software here. Let's look at some of the terms that are very frequently used in TDMs. First one is model years. So each travel demand model is developed for base year, interim year, and horizon year. Actually, many times there are more years, but these three are minimum that are always there in travel demand model. So they are collectively known as model years. So one term to remember is model years. Important notes about model year are as follows. Uh, a base year is typically an existing year when model is calibrated. So a base year is typically a year in which model is calibrated, and the calibration data is usually from past. So let's say we are looking at an MPO region, so we need to calibrate the travel demand model with the counts from entire MPO, so that needs to be AM and PM counts. So typically when the model is developed, uh, let's say the model is being developed in 2022, and let's say there are no COVID impacts, then typically the base year would be 2020 or 2021. So what happens between the data collection and the model year, the year in which model is being developed is it takes time to collect like a big area data and compile them and bring them together. Then it also takes time to figure out all the uh, roadway network and all the properties. And while we are working on the travel demand model development, a few year passes. So let's say we are trying to calibrate our base year. For an example, our base year is 2020, and let's assume that COVID impact is not there in 2020. Then most likely by the time we are done with calibrating, validating and everything, and when travel demand model is released, it might be 2022. So it takes a long time to actually build these models. It takes a long time to calibrate, validate them, and then predict, look how the future predictions look like, and then release it for the general use or public use. Several MPOs release them for public use, several MPO use them internally. In that case, they keep updating the travel demand model in-house. So that's a important point to remember. The interim year is typically 5 years ahead of base year. Um, so we have base year. Usually what we have is base plus 5 years. To analyze near-term demographic and transportation network improvement. However, in practice, the models are used several years after the base year when it was developed. So let's say our base year was 2020, the model got released in 2022, and when I'm working on project, let's say I'm working in 2024 or 2025. When I'm working in 2024 and 2025, I will consider the interim year as my base year, interim year as my, you know, kind of a base to see how good the model is. So what we will do is we'll take the 2025 model, which is for future, which was meant to be for future, but since we are already in 2024, let's say, if we are working on a model in 2024, then we will use the interim year model as our base, and then we will look at the counts in 2024 and then try to compare with the output with 2025 to see how good the model is performing. So in a lot of project, even though uh, it theoretically we should be comparing it with the base year, but by the time the models are developed and by the time uh, models are used, we usually end up going to 5 year ahead, which is the interim year model. So in practice, TDM model is given with a base year. Then we have interim year, which is base plus 5. And then usually we have a horizon or design year. Horizon year or design year, which is interim plus 20 years. Interim plus 20. So 20, we can also call it base plus 25. So let's say my base year is 2020. Then my interim year would be, let's say, 2025, and my horizon year will be 2045. So when I'm requesting a travel demand model, we can expect something like this. Or sometimes my interim can be 2015 and the base can be 2020 and the horizon can still be 2045. So it doesn't need to be exactly plus 20, but in general is plus 20 plus or plus 25. Now a horizon year is typically 20 years or more ahead of interim year, mostly 20 years, but it can be 25 years as well, but mostly in the increment of 5 years. So all these years are kind of uh, done in the increment of 5 years. So usually models are calibrated for the 5-year increment. So there are some models that are released in 2010, then the next release comes with the calibration of 2015, then the next release comes with the calibration in 2020. So usually there is 5 years gap and all the years get plus by 5. Horizon Year output includes the demographic and transportation network improvement for next 20 years or more. So in Horizon Year, we are looking at all the improvements and all the land developments that are already gonna be there. Most transportation projects aim to provide sufficient capacity through the Horizon Year. So most transportation projects are for future and it aims to provide the enough capacity through the Horizon Year. That's why the Horizon Year model is very important. So in the practical side of things, and if I can sum up the points we have discussed so far, so we have base year model onto which the when model was developed, the model is calibrated, and we do not have to do anything. So the travel demand model developer, whoever has developed the model, will use this year. So we usually, let's say, not touch the base year, or we there is something called model benchmarking, where we can look how good the model is doing on our base year. However, we do not play with base year as much. What we play with the entry year, because by the time we are using the model, we are already close to the entry year. So what we do is we look at entry year, then we look at our data, or let's say existing data, and then we figure out how close the entry year model output is to the counts. So by comparing the entry year model output with count, we will know how good the travel demand model is and what kind of adjustments are needed. And then we look at horizon year data and horizon or design year, let's say, and then we use this to do our capacity analysis or traffic analysis later on. So we develop the volume based on horizon here, and then we work with the traffic operations and do many other things. So for example, if a TDM is built in 2022, it would likely include 2027 as the base year, and then 2050 as the horizon year. So 2027 as the interim year and 2050 as the horizon year. Like I mentioned, it's usually in the increment of 5, but here let's say the base year is 2022, then it will be plus 5 for the interim, and instead of 2047 is usually a multiple of 5, so 2050. So this is kind of a general uh, timeline of how these years are built, just to give an background on what to expect when we are opening the travel demand model for the very first time. Traffic volume forecast for any other year that is close to typically within 5 years of interim and horizon years are obtained by interpolation of volumes. This is another important point. So let's say uh, our MPO model is giving output for 2045, but for the roadway project we need the design year to be 2047, for example. So what we do is we cannot go and build another model for 2047. It's difficult as it is to use 2045 model. Travel demand model takes a lot of time and resources to run. So what we do is we figure out the volume in our existing counts, and then we figure out the volume in 2045 counts, and then we figure out a linear growth factor between. So let's call this existing, or even comparing with interim. So let's call this existing count, this is horizon count, which is 2045, and we are trying to forecast it to 2047. We just linearly interpolate it at each point to get to 2047. So one assumption for linear interpolation, let's say anywhere between 2040 and 2050 if we need this uh, volume forecast for any years in between these 5 years minus 5 year plus from 2045, we will just linearly interpolate the growth rate. So it is assumed that transportation infrastructure would not vary significantly in 5 years, and travel demand pattern will remain the same, and everything will kind of remain the same. So a linear interpolation of number would be sufficient under the assumption that transportation infrastructure would not vary significantly. Also, along with transportation infrastructure, another assumption is the land use will kind of remain similar within the 5 year in the horizon. So that's an interpolation for the using the horizon year from the models for the nearby years. And TDM output can provide equilibrium link flows. We will look at what equilibrium link flows means. We already look in traffic assignment on how this equilibrium link flows are calculated, but we'll look in more depth about equilibrium link flow. But the link flows are given for AM, midday, PM, and nighttime peak period. The important point to note here is the link flows. This is an important point. So usually from travel demand models, what we get is directional link flows. So a travel demand model, let's say for we are looking at AM peak, will give us how many vehicles are going in this direction during AM peak and estimate number of vehicles. But it does not tell us how many vehicles are turning left, how many vehicles are going through, how many vehicles are turning right. So what travel demand model output gives is usually the link flows. And if we want to calculate the turning moment count from travel demand models, we can do some tricks. We can generate a bunch of smaller links which are directional, but then the accuracy of the model goes down. So what we usually get from the travel demand model is link flows, and for most cases we need to estimate future further volumes based on the link flow. So based on the links flow, we might have to calculate turning moment counts or some moments which are not there in the travel demand models. The second concept to discuss here is the geography. So how is the geographical area, which I'm calling land use for a long time, how the land use is coded in the travel demand model? So a travel demand model typically consists of TAZs, which is traffic analysis zones, also simply referred to as zones, transit network and roadway network. The TransCAD file used to represent the geography is as follows. A TAZ file is an area with polygon and has a .dbd extension in TransCAD. So a TAZ files are just area polygon. So this is one TAZ, this is another TAZ, let's say this is another TAZ, this is another TAZ, and this is another TAZ. So these are all polygon files, polygons, and they are kind of contained in one single file, and this single file is saved with .dbd extension. And in TransCAD, when we open this DVD extension for TAZ files, the layer name is shown as polygon layer. Next one is the roadway network. These are link node structures coded as points and lines in the same file. So, oops, where were we? Oh, here. So the way roadway network works is roadway network, like we have seen in past, is a structure of nodes and links. So there is a link connecting two nodes, then a link connecting two nodes, and link connecting two nodes. Now these links can be two directional or one directional, defined by the unique ID that is given to those links. So a ID 1 means the direction of flow is in the direction where in which the link is drawn. ID number -1 is the direction of flow is reverse of the way link is drawn. I will talk about it. And then ID number 0 means this link is bidirectional. So this is how the roadway network is represented by drawing bunch of nodes and links. Now these nodes can represent an intersection of two links. So a node can be used to uh, have like multiple links coming together, or a node can be used to draw the geometry. So this can be just a dummy node, or just to connect different points on the links. So a node can have multiple links, or a node can be just kind of a dummy node just to draw the curvature or just to draw a roadway geometry. Usually a links are straight line in TransCAD. So let's say I want to draw this road in TransCAD. So the way I will draw here is one node here, one node here, one node here, one node here, and so on. The transit system coding may include local bus transit, rapid bus transit, light rail, heavy rail, etc. So transit rail have an extension of .rts. Some of the transit routes, for example, bus routes and non-exclusive right-of-way routes, which is like local bus route or some of the bus rapid transit, are drawn on top of highway network. So some of the transit overlaps with the highway network, whereas some of the transit, for example, rails which have exclusive right-of-way, are drawn separately, and those are saved in .rts file. Working with transit in TransCAD is kind of a little bit tricky. It usually throws a lot of errors, and we try not to mess with transit unless we have to. Further details related to 3 geography file is provided in next section. So these three are 3 core geography files that are used in travel demand model in using TransCAD. So for traffic analysis zone files, TAZs are smallest unit of the land area with similar characteristic considered in the TDM model. Uh, TAZs are drawn primarily based on census tract. So the first source is the census tract data. Let me draw, because we have the population and different kind of information within the census tract. So the first source of defining TAZ is census tracts, because a lot of data can be easily ported to this TAZs. So if we have a census tract, we likely try to keep that as TAZ. Then second one is major roadways. If a major roadway passes through a region, so usually census tracts are also divided such that major roadway lies at the boundary. So major roadways kind of constitute one side of TAZ's boundary. Sometimes minor roadways as well, and then natural boundaries such as river and creek. So figure 3.10 represents the TAZs used in TDM model. So this is an illustration of how the TAZs are drawn. So we'll notice there is a river here, which is how some of the TAZ boundaries are defined. So TAZ's boundaries are cut off at the river, and let's say usually I have drawn an hexagon, but they don't need to be an hexagon. They can be any shape. Usually they are very weird shapes. So these are usually census tracts, and we carry it forward to TAZs. Then there are natural boundaries like this river, and then natural boundaries like this major roadways. So major roadways are most likely constitutes the uh, boundary of the TAZs, and minor roadway most of the time they also constitute the boundary of TAZs, but not always, whereas major roadways almost always constitute the boundary of TAZs. So boundaries of TAZs are typically located along major and local roadways. All major roadways are likely to be a TAZ boundaries, but not all all major roadways are likely to be TAZ boundaries, but not all local roadways are TAZ boundaries. Size is dependent on the population and employment density. That's another factor. So what we have is We want the TAZ to be a sector of homogeneous kind of characteristics. So when the population density increases, then we have to divide the area into smaller groups. So let's say this is the downtown area. Let's say this is the downtown area. Let me change the color here. So let's say we are looking at this downtown area. Then since population density in downtown area is larger, we will have smaller TAZs. Then when we go to suburban area, which is mentioned here, in suburban area, houses are spread apart, so we will have larger TAZ area size. So the size of TAZ, when we look at it, depends on how dense the area is. So if we are looking at a map and some locations have smaller TAZs and some locations have bigger TAZs, that kind of gives an indication on how dense the area is. It is smaller in density populated areas of the city such as downtown. So TAZs is smaller in densely populated area of cities such as downtown and is larger in suburban area like I mentioned. The actual travel demand model, also known as TDM, consists of thousands of TAZs. So this is just for illustration. In previous video, like I mentioned, the number of TAZs we are working on in most of the travel demand models are listed in thousands, most likely between 2000 to 10,000 TAZs. So from practical side of things, it's kind of good to know these numbers just to see the scale of what we are dealing with. TAZs contain socioeconomic data such as population, household data, which is household size, household income, number of household in the area, income, household size, employment, etc. So TAZs contain a long list of data like I mentioned before when we were discussing trip generation method, and these are just some of them. They also contain vehicle ownership and several other household characteristics. TAZs are used for trip generation and trip distribution purposes. Driver behavior. So in the next paragraph, we are going to discuss the importance of area type. Let me define what is area type first. So the travel demand model usually is built for the dense part of the city and also the suburban part of the city and a little bit outside of the city. So let's say in this particular example, let me reload this real quick. Let's say in this particular example, this is the dense part of city and this is the downtown area. So we will call it urban or urban core. So this part of area is called urban or urban core. Urban or urban core. Whereas as we move away from the dense part of area, let's say here, so we are moving in suburban area. Now if we move a little bit further, this is a study area kind of boundary, but the actual travel demand model can be much bigger. So let's say the travel demand model boundaries are here. This is my actual model boundary. So there will be some areas a little bit outer side and there will be rural area. So an MPO model and statewide model usually contains the urban core, suburban, rural. Now these area types are important. So when drivers drive in an urban area, they typically drive very close to each other, and the link has higher capacity in the absence of signals and everything. Whereas when they drive in suburban or rural area, they drive a little bit far from each other. The driver characteristic changes when they are driving in urban area versus when they are driving in rural area. So that's the importance of area type. Area type plays a role in how drivers drive in certain area type. So the next paragraph goes in and discusses the area type. Driver behavior changes significantly depending on the type of area they are driving in. In general, the driver drives more closely to each other in urban areas than rural areas. Hence, for similar roadways, the speed and capacity varies based on the area in which roadways are located. So like I mentioned, the driver behavior is dependent on what kind of area they are driving in. So the link capacity and speed will depend on the roadway type. Sorry, the area type they are driving in. So an undeveloped area may develop in future, leading to a change in area's characteristics. So what happens is, let's say this is suburban area and this is our existing map. So in future there will be more development and the smaller TAZs may come in the future, and this rural area might become suburban area. So now what happened is, the area type changed. So urban core will likely still be urban, but suburban might change into urban, and rural might change into suburban, or rural might change into urban, or any other things can happen because of the land use patterns. Because of the changes in land use pattern, the area type can change in the future. So what we cannot do is use the link speed and capacity from the existing data. So let's say I have this existing roadway and I have some speed and capacity. The speed and capacity is dependent on the area type, and in the future the area type itself can change. So even if there is no changes to the roadway network, because the driver characteristics will change, the speed and capacity of a link will change. Is that clear? So let's say I have a roadway in existing and I have exact same roadway in future. Nothing has changed. So we will assume that the speed and capacity kind of will remain same. However, the property of this link is dependent on the area type. So let's say in existing, this is a rural area. So the speed and capacity of this link in rural area will be different than, let's say we are going in future and this has become urban area. So from rural, let's say there are more development and now we are in urban area. So for the exact same link, the speed, capacity and other characteristics of the link will change. That's why we need to have a formula to relate the land use type to the speed and capacity of the roadway. So the speed and capacity and other characteristic of the roadway is not only dependent on how the roadways looks like, whether there are two lanes or the shoulder width and stuff. It also depends on what kind of area it is in, because drivers drive differently in different areas. So the next step is to automatically classify this area. We cannot go in travel demand model and look at, let's say, 5,000 TAZs and try to figure out whether it's rural or urban. It's very difficult. So what we do is um, we have 5,000 zones in existing, then 5,000 zones in interim year, then we have, like, let's say 5,000 zones in a future year, and all of them are with different characteristics. So in existing characteristics will be different than interim characteristic, will be different than horizon year characteristics. So we cannot go and code them one by one on what the area type is. So there is a factor which defines the area type. It's called TAZ density factor. It looks at the density of population and employment in the area and tries to automatically classify what a land use is. So this is the first process called initialization in the travel demand model. So given the potential changes in area classification of a large number of TAZs between model years are base year, interim year and horizon year. So given that there are potential changes in the area classification, the area types are dynamically assigned within TDM. They are not manually coded. So the way to define the uh, TAZs, the way to categorize the TAZs dynamically is given here. So TAZs are divided into various area types based on population and employment density. So TAZ density factor is TAZ total population plus study area population divided by study area employment. This is just a formula I took from CAMPO. CAMPO is Capital Area Metro Planning Organization, which develops TDM for Austin. So this is from CAMPO. Different MPOs may come up with a different equation. This is just one of the example on how we can combine population and employment, and then divided by the total area size to figure out the TAZ density factor, or it's an equivalent factor of population and employment, considering both. And then based on these factors, we can categorize the TAZs into the following uh, one of the following categories. So the first one is CBD, Central Business District, which is usually downtown, urban intense, urban residential, suburban residential, and rural. And these are the factors from Campo model. Depending on what equation different models are using, these numbers will change. So just kind of wanted to give an overview of TAZs and the importance of how the area types are defined. So area types are not coded manually because they may change from different models to different models. They are dynamically assigned based on the population and employment density. And based on the population and employment density, an equivalent factor is calculated called TAZ density. And using the TAZ density, we categorize them into different categories. These factors by no means are what is standard. It will change from every MPO to every MPO. Even this formula will most likely change from MPOs to MPOs. The big lesson learned from this one is the TAZ area type is not a constant thing. It changes between the models, and since the TAZ area changes, the roadway characteristic changes, so we need to dynamically define the TAZ area type, which is done in TDM models. So far we looked at the implementation of travel demand model. We looked at the model years, and we discussed several practical things that are important to know about model years. Then we are looking at geometry. Within geometry, there are three files: TAZ files, roadway network, and transit files. So we looked at TAZ files so far.